welcome to yet another lecture about the inclusive advanced studies for the people which are not from SU. This is an initiative from our university, initiative of Italian. Excellent. We have talks every week on 12:15, and the talks are divided into ideas and lectures. Ideas are from some young scientists that are students of IAS, and lectures are from more senior scientists like Gudrun that already demonstrated the understanding, and they give lectures for that. It's supposed to be like a documentary, so even if you're not from the field, you should kind of try to understand things, something like that, and have fun with it. It's like a live documentary, right? So often I'm being asked, why should I go? It's not my field. You spend a lot of time, hopefully being a researcher, to look for documentaries and things like that. Like now you have a possibility to watch one live and to ask questions, so that should be fun. After this, there will be a little reception upstairs, some figure food. So I will say now, and I will say also afterwards. So feel free to come upstairs. Just take the stairs up as soon as you come, and you're going to come upstairs and have the possibility to chat with Gudrun, and there will be more fun. We'd also say that Gudrun has been very polite to accept our invitation to do here, and this is in the middle of our winter school in theoretical physics. And Thomas, me, and Kayla, and Heidi are organizing. And this is actually fantastic. It's actually the first time we tried this synergy. So I think that should cover why you gave today. And now a few words about Gudrun. I know her since a while. And she had a PhD from Hamburg and Daisy. Then she has held a position, if I can open my thing. I already know by heart, but very nice. Look very professional. Then she has been positioned at Stanford Linear Accelerator, at Munich University, at CERN, and now is a professor at the Technical University of Dortmund and as postgraduate group. She's famous for polymer physics, and I'm sure that you will know a lot about that here, which is a particular part of high-energy physics, but contributing a large for understanding fundamental equations. So it's a pleasure to have Gudrun, discussing that for you.
Thank you very much. I'm very honored to be here on this part of this lecture, and I hope I can tell you something about the excitement of my field, which is vapor physics. So let's start with something. It's not browsing. It's not doing that. Okay. I don't know. Maybe somebody can fix that. Well, it fell asleep. Okay, very good. No, thank you. Okay, so so I was asked to talk about what I'm doing as a scientist. This is what I'm doing as a scientist. So this looks very familiar. These are free fruit. Free fruit. And from a scientific perspective, you can say, well, these are three objects that belong to the same kind. They are all free fruit, yet they are different. And they differ by all kinds of things that we can detect as humans. We don't even need a detector for this. So they have different colors, and they taste different. And the magic word here, of course, it obviously comes to your mind, is they have different flavors. One is an apple, one is a pear, and one is a banana. So, but this theme will be, of course, throughout this whole talk, and this is just an analogy, with something that is very familiar to our everyday experience. There are things of the same kind, so we can even put them in the same basket, and then maybe say that, well, from a broader perspective, maybe they're the same. They are all fruit. But of course we know the symmetry among the fruits is spoken by flavor. Okay. So this is one of the big themes in particle physics, that we study symmetries and symmetry breaking. And this was just a very bold, everyday experience example for illustrating this. Okay, so things have similar features, but yet at some level, this symmetry, which was very helpful to describe food, there's meat, there's pasta, and there's fruit. From this perspective, it's fantastic, it's perfectly okay to say these are the same things. But of course, if you really want to eat them and you have some kind of flavor, you will notice that there's breaking of symmetry. And the other thing that's very important to particle physics is, of course, the strong desire for simplification. We want to describe nature with a minimal amount of degrees of freedom. We really want to go down to this microscopic level as much as we can. And this is, of course, this is a very old enterprise. This has been started already by Aristotle, who had a very simple proposal for a standard model of particle physics. At that time, he only had 5 elements: water, fire, earth, air, and ether. And this, of course, has been improved over the years. And a couple of 100 years ago, we started to develop the periodic table of elements, which at that time had only 66 elements, but by now it's an enormous thing. It has more than 100 elements, and it is very useful for chemistry and for biology. But of course, as a particle physicist, or even as an atomic physicist or a nuclear physicist, we would say, well, this is a useful collection of elements, but we know already that at the microscopic level, the elements are not fundamental. Elements are atoms, and atoms are composed out of nucleons, and nucleons are composed out of quarks and gluons, and even in the atoms there are also electrons. So the fundamental degrees of freedoms are not the elements in the periodic table. They started with the onset of particle physics, where we discovered the electron, where the proton was discovered a little later, but now we know it's a nucleon. It's not fundamental anymore, but we have a muon, we have antiparticles, we have neutrinos, we have quarks, and all kinds of phenomena that come with it. So this is, I would say, these are the basic driving forces, in particle physics, that we consider symmetries because they help us to organize the very few basic ingredients that we are after. Okay, so what, can you do that again? And I try to not to stay too long on one table. Okay, so the standard model of particle physics. This is our periodic system with the few ingredients that we consider as fundamental today. And as a very practical definition, I would say it's the most economical framework that describes data. Okay, and data, this is just a collection of data, so this is, you don't really have to read it, and there are longer and longer tables of stuff. So data really means that there are observables, and then there are measurements, and then you can compare the measurement to the prediction in this standard model. The standard model is our fundament, is our theory of the degrees of freedom that we consider as elementary today. Okay, and this standard model, of course, has evolved over the past decades, and it has passed tremendous tests. It's taking at face value, experimentally challenged, but not ruled out. There's no hard evidence that it is wrong. It's been tested at the LHC. So this is an experiment that takes place in the Geneva area. So this is a snapshot, and the experiments are underground. This ring here is the Large Hadron Collider, so protons are colliding head-on in these detectors. So there's one experiment, it's called CMS. There's one, it's called LHCb. That's the one that I will report results from later on. There's Atlas, and there's Alice. So this whole enterprise is underground. It's a multinational enterprise, and it's running now. So we are very much interested in that. Yes, there's a question.
Why is the standard model economic?
It's economical in the sense it has the least number of parameters. So we want to have a description of nature with a minimal input, with the minimal input that we give in. You can describe, I would say, it's with this periodic table. The periodic table is an excellent description at a certain energy level for chemistry, and it's the right degrees of freedom. But for high energy physics or shortest distances, we have other degrees of freedom, and that's the level of sophistication we came up with. So it should be something simple. You want to have a fundamental theory that doesn't have 10,000 degrees of freedom. Then you think, okay, so that by 10,000, I mean, there must be some symmetry among them. Okay, so that's the standard model, and it's being tested at the moment. And let me remind you a little bit what it is. It's a quantum field theory in 4 dimensions, I mean Minkowski space, 3 space, and 1 time dimension. And it has a local symmetry. All the interactions are based on local symmetry. So there's a strong interaction, SU3 color. There's the electroweak interaction, that's the product of these two, SU2 left cross U1 hypercharge. That's the basic symmetry of the standard model, and that's the symmetry that's responsible for the strong, the weak, and the electromagnetic interaction. And this interaction is between matter, and matter are quarks and leptons, so they have spin 1. And then there's also this famous Higgs particle that has been discovered in 2012, which is spinless. So if you write this down, everybody is massless. To get masses, you need spontaneous breaking of this electroweak symmetry, which is communicated by the Higgs particle to the standard model. So fields get their mass from coupling to the Higgs boson. Okay, so this is the standard model on 1 page, and it's even, if you want to write it down as an equation, it's 1 line. This is what I mean with it's really economical. Of course, this is a very abstract notation. So this F squared term, this is a term that tells you how the force carriers, the gauge bosons, the gluons, the photon, the W's and the Z, how they travel and how they interact with each other. And this term tells you, so psi is a fermion, and how fermions travel, so they have a kinetic term, but they also interact with the force carriers, and that's in this capital D. This is a covariant derivative, and there's a gauge field hidden in that. And there's a term, that's the kinetic term of the, so phi is the scalar of the Higgs boson, and this term also gives masses to the W bosons and the Z bosons. These are the massive bosons, the force carriers in the standard model. Okay. And this term is the one that gives mass to fundamental fermions. This term is responsible in the standard model for the electron mass, for the top quark mass, for the masses of all the fermions in the standard model. And it is a coupling between 2 quarks or 2 leptons to the Higgs field, and the coupling strength is in this Y coupling. Okay, and we will come back later to this, because this is linked to this flavor physics topic. Okay, so this is the only link, if you wish, to the flavor topic. But it's 1 term in this 1-line equation, which is it's very condensed notation, but this is the fundamental equation of nature, of the standard model, of particle physics, and it describes really many phenomena. Okay, so it's I think it is kind of economical. Okay, so this is where we are. So this is energy scale, it goes up, it's a logarithmic scale. Okay, and at some point you might draw, but you don't have to, but you can say, well, maybe this is nuclear physics and maybe this is particle physics, but you can draw the line. I mean, you can move this line around, and it's more like at some point you start, okay, let's discuss about particle physics. So I kind of thought maybe it's the energy, the binding energy of the deuteron of the QMV, which it's maybe the answer for particle physics. And then there's the next scale, that's relevant to particle physics. It's the binding energy of the strong interaction. It's a scale of QCD. It's somewhere around a few hundred mega electron volts. Okay, and the next scale that we have seen in particle physics is the scale which has this complicated name of electroweak symmetry breaking. It's the scale when the Higgs boson gives mass to fermions and the massive force carriers, the masses of the Z bosons and the W bosons, which is around 100 giga electron volts. Okay, so these are the fundamental scales of particle physics that we have seen, and here I put the particles with their names where they are roughly their masses. So the lightest particle here is the electron, which is sub-MeV mass, and then there's the first generation of quarks, the up and the down quarks, and a little bit heavier is the second generation, the muon and the strange quark, a little bit heavier, the tau lepton, the charm quark, the B quark, and the top quark. That's the heaviest fundamental particle that we have seen today, that we consider this as fundamental as of today. I recall this is an experimental question whether we consider a particle as fundamental. Some time ago the proton was considered as fundamental, but now we know it's composed out of quarks and gluons. So according to current state of the art, these particles here are consistent with the assumption of being fundamental. The heaviest of these particles is the top quark, 175 giga electron volt. And I also am putting here the masses of these electroweak gauge bosons, the W's and the Z. They are a little bit lighter. And then we have the Higgs boson here. It's 125 giga electron volt. And if you wish, this is the home of the standard model, because this is where we have done many, many experiments, and we have developed this standard model, and it's consistent with data. And this shaded area here is the region that we want to, the territory that we want to explore with high energy experiments and more precise searches with precision experiments. So this is the area of the unknown, and if you are using this uncertainty principle, I mean the Heisenberg's relation, then you can link energy to time or link energy to distance. And if you want to have it in meters, this is as small as 10 to the minus 18 meters and even smaller. These are the distances that corresponds to the energy scales that we are exploring at the LHC. This is the TeV scale, the tera electron volt scale. Okay, so this is what we want to test. And of course we want to test the standard model because although we are very happy about it and it's very good, it has a couple of deficiencies, and I'm just giving here a list. Okay, so there's the issue how to accommodate dark matter. Baryon asymmetry of the universe cannot be explained with the standard model. We have three gauge couplings. Is there a relation between them? We have the coupling of the strong, the weak, and the electromagnetic coupling constant. There's no gravity included, and the topic I want to allude here further in this talk is this flavor puzzle. So the flavor puzzle can be seen already here. There's the top quark, and there's the up quark. And from a symmetry perspective, they are both the very same thing. They are both fruit. But apparently, they are in very different places in this plot. Their masses are split by 5 orders of magnitude. So apparently it's not the same fruit. There must be something different. So what is it that makes these two fruits so different? That's the flavor puzzle. Okay. Oops. Okay. So, but to sum up, the standard model is a really wonderful creation. And but it has to face these questions, and because these questions are beyond the standard model, we are looking for physics beyond the standard model. This is why we are improving experimental precision and try to reach into higher energies to test the standard model, because given all these facts, it seems that it has to break down at some point. So what's coming back to these a little bit to flavor. So I'm reminding you here of this fundamental one-line equation of our description of nature. And let's just reconsider how economical it really is. So we have three forces: the strong, the weak, and the electromagnetic. So let's just count the number of parameters that we have in our theory. So how many parameters do you have to measure to describe everything? Okay. So we have 3 gauge couplings to be measured. Something sets the electroweak scale. That's, for instance, the mass of the Z boson. That's one parameter. And you have to know something about the scalar potential. It's just 5 parameters. It's really cool for fundamental theory. But then all hell breaks loose in the fermion sector. And that's related to this term that we talked about earlier. That's the term that gives masses to fermions by coupling to the Higgs. 13 new parameters are coming in. So this looks not so nice as the other sectors. So we come up with in total 18 parameters, and this is still kind of minimal counting, so I was ignoring neutrino masses. We know that neutrinos are massive, but we don't know exactly from which mechanism they get their mass, so I left it out here. Okay, so it seems that the flavor sector is the least economic sector of the whole standard model. And maybe this is where we think there's room for improvement. So if you have many parameters, you think maybe these are not the right degrees of freedom and maybe they're just the same, but you just have to figure out what tells a banana from an apple. Okay. So this is where we are with flavor. And so how comes flavor in? Okay, so we have here fermion fields, for instance, two quarks that couple to the Higgs boson. But quarks, like leptons, they come in generations. We have a generational structure observed in nature, and that's part of the standard model. We have first, second, and third generation. So all of these psi fields that we have in this one-line equation, they get an index, and the index goes from 1 to 3, counting first, second, and third generation. And we label them usually according to their mass ordering. So the first generation is the lightest, and the second is a little heavier, and the third is the heaviest. For instance, the up quark is the lightest, it's first generation, charm quark is second, and third generation is the top quark. Okay. And this seems to be not doing a lot, but actually it gives rise to an enormous onset of phenomena. And this arises because this coupling here, if these fields here, psi, are vectors in generation space because they carry a generational index, it means that this object here, this coupling Y, is a matrix now. And it doesn't have to be diagonal, it can have off-diagonal entries, and that means fermion generations, they can mix. They mix and change flavor. This is actually what they do, and they do this in weak processes and only in weak processes. This is not happening in just QCD, the strong interaction. You need the weak interaction for particles to change flavor, and there is this phenomenon of CP violation related to this very matrix. Okay, so shown here are again first, second, and third generation, just the up-type quarks, up, charm, and top, and the down-type quarks, down, strange, bottom. And if you have a weak boson, it carries electric charge. So if the top quark emits a weak boson, then it can decay into this weak boson and a weak quark. This is within the same generation, but it can also decay into a strange quark. And it can also decay into a down quark. So all of a sudden we have these intergenerational transitions happening, and the relative strengths, I mean, how often does a top quark decay to a B quark versus how often does it decay to a top quark? You can read out from this Kabibo-Kobayashi-Mascara matrix, the CKM matrix. So it's a hierarchical matrix. So on the diagonal is roughly 1. So decays within the same generations are preferred, and then you go further away. So lambda is a small parameter, so the larger the power of lambda, the further suppressed it is. So the coupling from top to bottom is here, this is 1, the coupling from top to strange is lambda squared, and top to down is lambda cubed, roughly. So there's a hierarchy, there's very strong hierarchy in this mixing. And I'm just giving you here the hierarchies, but this matrix is mapped. It's measured, and some of its entries are measured with extremely high precision, below 1%. Some are a little less measured. This is an active program at the LHCb experiment to measure, to understand these mixing better and better, because the better you understand parameters within the standard model, the better you can test or look for deviations from the standard model. So, but what is it with the fruit and the flavors? So now we have 3 generations, and these are apparently very different objects because they have different mass. Okay, but their coupling to the gauge interactions, so the strong, the weak, and the electromagnetic one, are exactly identical. So there is a symmetry. For the gauge interactions, do I need to do? I have to press once more. Okay, so for the gauge interactions, they are the same. The gauge interactions don't care about which generation they are coupling to. However, we know that, okay, but these things are not the same because they have different mass. Okay, so this is the flavor. What flavor does to your model. It's not working. Maybe. No? Okay, very good. So this is again the plot from before. We have this quark, we have the spectrum, the up, down, strange, charm, bottom, top quarks. So here you have the masses. You can actually see the up quark mass is around 3 MeV, and the top quark mass is much, much heavier. There's 5 orders of magnitude, although they're exactly the same for the gauge interactions, for the fundamental forces. Okay. And so one can even include mixing. So all the flavor, all the distinction between the different quarks is encoded in the standard model in this Y matrix. And you can, this is a little bit simplifying, so there's a Y matrix for up-type quarks, and there's a Y matrix for down-type quarks, and there's a Y matrix for leptons. And so these are fundamental parameters, and I wrote them here as determined by experiment. So this is the up-type quark Y matrix. And just look at it. So there's an entry that's almost 1. This is the one that's responsible for the mass of the top quark. Actually, its coupling to the Higgs is roughly 1. This is a very natural number. If you have a dimensionless coupling, that its size is around 1. But all the other entries are smaller. Okay, so there's 2 orders of magnitude smaller. This is roughly the charm quark. But we have very strong hierarchies. We have numbers as small as 10 to the minus 8. And we have imaginary parts. These are the ones that are responsible for CP violation. Okay, we have different signs. Okay, and we have also the masses for the down quarks. They are encoded in this Y down matrix, and it's very hierarchical. So this is first, second, third generation. For the charged leptons, first, second, charged generation. So if you look at these numbers, I mean, do you think these numbers are just random, or is there a structure? So if you think there is a structure, you would think, okay, let's find out what structures these numbers. What is the mechanism that makes them so hierarchical? I mean, if you have 3 things of the same kind, of roughly the same kind, you would think maybe their mass should be similar. I mean, just go back to our food example. So the weight of a banana and an apple and a pear, they are roughly the same, okay? But this is not so for the quarks. For the quarks or for the fermions, each of them they have exactly the same couplings to the interaction, but the mass is very different. Okay? So there's a strong hierarchy. I mean, to me this doesn't look like, I mean, it looks too much structure to be an accident, but this is my opinion. You can still say, well, this is how nature made them. Okay, but for people thinking about flavor, this is a serious puzzle. Why these numbers look the way they are. These numbers are measured. They are not predicted in the standard model. They are parameters of the standard model. So within the standard model, we are all fine. We measure them and then we can make predictions. But we haven't understood actually what makes these numbers look this way. And this is a very deep problem. This is the flavor problem. And I have no answer to this. There are proposals explaining these hierarchies, and I will also come back to this and tell you how to can maybe check these proposals. But there is no, I mean, agreed answer from the whole community to the mechanism that produces these numbers. Okay. But still what you can do, since this is all measured and the standard model is very predictive, you can actually go on and test the standard model. Now we know its input. No. Oh, it's still going. Very good. Okay, and we test the standard model with its feature. And it has a feature that's called universality. And universality is exactly that fermions are all fruit. Namely, they all, irrespective of the first, second, and third generation, they have the same couplings to the gauge bosons, to the interactions. Okay, they differ in mass, but they have the same interaction. So now we do this not with quarks, we do this with leptons, and this is apparently what comes out of what's useful experimentally. So now we have the electron, the muon, and the tau as our flavors, as our lepton flavors. And the standard model predicts they couple exactly identical in the same way to gauge bosons. Now, there are two interesting anomalies that exist since 2014. And they are driven by this LHCb experiment, but also previous experiments, so-called B factories, have worked on this. And I want you to learn a little bit about these anomalies because I find them very fascinating. And of course, these are anomalies. This observable RK has measured with some significance of 2.6 sigma away from the standard model. 2.6 sigma is not much, okay? But it can easily be statistical and go away. But if it stays, it has enormous implications. So if you are a theorist working on this field, you shouldn't be waiting for 10 sigma. Okay, so I want to talk about a little bit about this anomaly, and RK is a ratio of branching ratios. There's a B meson, it's a bound state of a B quark that decays to a bound state of a kaon, that's the bound state of a strange quark, and muons. And you divide this branching ratio to the same thing, but instead of muons, you are measuring electrons. So if muons and electrons would be the same, under the gauge interactions, this ratio would be 1. So LHCb hasn't measured 1. So this anomaly looks for differences between muons. This observable looks for differences between muons and electrons. There's another one, it's RD or RD star, depending on whether this D meson here, it's a bound state of charm quarks, is a vector or is a pseudoscalar. And it compares tau leptons to all the other two, the lighter two generations, the electron and the muon. And for the vector, it's a 3.4 sigma, and for the D, it's 2.1 sigma. So apparently there's something in the data that's not perfectly consistent with the standard model that we observe in meson decays, in quark processes, into leptonic final states. So we are probing one of the hardwired concepts of the standard model, whether leptons are actually coupling universally. So let me talk a little bit about RK. So RK, so LNU, lepton non-universality, you can define this even more general. The kaon is just that you can use for, but you can also use a K-star or an inclusive final state. And all models which couple universally to leptons, so for which these leptons are all good, including the standard model, this ratio is 1. And this is to show you a little bit what particle physics actually the status. This is the branching ratio for B2K into muons, as measured by LHCb, the experiment at CERN, one of those. And it's a branching ratio at the level of 10 to the minus 7. So we are measuring here processes. If you have, I mean, you need 10 to the 7 reconstructed B-mesons to have one on average decay into this mode. So to have statistics here even on the uncertainty, you can imagine how many, what event rates you need. Okay. So this is the measurement of LHCb, and you can compare it to the standard model prediction. It's the right order of magnitude, and it agrees, although the standard model is a little bit higher, but you notice immediately the uncertainty of the theory calculation is way bigger than what the experiment has measured. And this is the evil thing that comes up once you do physics with quarks. It's bound state. Quarks are not decaying, I mean, in the lab, they are decaying within this hadronic medium. They're decaying in these B-mesons. Okay.
And somebody to blame are these people here in the lab.
This is where you should be working on if you are in lattice field theory. So these are form factor uncertainties for the experts. Okay. So they are much bigger than what the experiment can do. So if you're just comparing these two numbers, you wouldn't be thinking about new physics or breakdown of the standard model because of these large uncertainties. Now you can go to the B2K EE mode. LHCb has measured it as well. And the uncertainties are a bit larger because electrons are more difficult for them. The standard model prediction is the same because the standard model couples universally to leptons. And but again, just comparing these two numbers, you wouldn't be able to claim any BSM, any physics beyond the standard model. Now you can do the ratio, and this is what LHCb finds. So it's something like 3/4 plus minus 10%. It's below 1. So the nice thing is here, we can use this symmetry of the standard model, the universality, to write here a 1. And it's not a 1 with uncertainties like this. And this is just, of course, in the both numerator and denominator, there are large uncertainties. But they have to cancel exactly because the standard model couples universally to the leptons. So now with this ratio we are able to say something because we can get rid of these nasty uncertainties. So this is the experimental situation. This is RK, this is 1. This is the standard model in pink, and in blue and in red are previous measurements of RK. So RK is measured in some kinematic distribution. It's the invariant mass of this dilepton pair. And this tiny thing here in black, this is the LHCb result. So it's 2.6 sigma below the standard model. And this creates a lot of excitement. So,
Question?
yes.
What is the red cross to the upper right?
The red cross, that's a measurement by Barbard. It's a previous experiment. And you see it's consistent with the standard model at 1 sigma. So all previous experiments, like the blue one, this is Bell, this is an experiment in Japan. And the red one, this is an experiment that was running at Stanford. They didn't have the sensitivity. Their uncertainties are much larger than what LHCb is doing, and their results were consistent with the standard model. So they did measurements, but they didn't have enough events. So they could prove that one can measure this, but they didn't see any deviation. So the new thing here is this black cross, and this is LHCb. Okay, so it's clear that also LHCb could in principle measure this for higher values of Q squared. This would be a very nice consistency check. Okay. So having this, we would like to explain this? Okay, if you're in phenomenology, you immediately think about how can we explain 25% deviation from the standard model in this ratio? Is this even possible, given that we probed the standard model with such high level of scrutiny? Okay, so if you are doing all the math, you figure out that there's this decay amplitude from a B quark to a strange quark and 2 leptons in the standard model, and to get this effect, this suppression of RK, you need 25% correction on top of the standard model amplitude. So the standard model is really well tested, so how can you do this? And the trick is that this process here, from a B quark to a strange quark, this can be mediated only through a quantum effect, through one of these loop processes. Okay, so you need the weak interaction to change flavor, but you need you need to do this twice. You need to change from a B quark, for instance, to a top quark, and then from a top quark to a strange quark. So it's at higher order in the weak interaction. In the standard model, this is why it's only 10 to the minus 7 branching ratio. Okay. So, and the easiest idea to get a large effect on something that's a quantum effect, that's a loop process, is to add something that is happening at tree level. And the most direct model that you can write down in this situation is a model with so-called leptoquarks. So leptoquarks are hypothetical objects. They are not existing in the standard model, and they couple quarks to leptons. So this is a quark, this is a lepton, this phi is a leptoquark, and it has a coupling matrix. So this is then the Feynman diagram for this. So there's a B quark, and it decays into a lepton, and there's a coupling here. It says B quark and lepton. This leptoquark phi is exchanged. It has a mass m. Okay, and then it decays to the lepton and a strange quark, and it has the coupling strange and left. So there's always this generational index in this coupling. And if you do this, actually, you can do lots of things. Well, it actually works. You can explain RK with these type of models, and it's very predictive. You get a mass range from 1 to 50 TeV. So if the mass is 1 TeV, it would be really nice if it's around 1 TeV. You can look for this particle. That's an explanation of this anomaly at ATLAS or CMS, at the other experiments at the LHC. And you can, for instance, look for these particles through their decays. Now that's where things become model dependent. It depends what are the interactions of this leptoquark. If it is a vector under the weak interaction, then these type of decays can happen. If it is a triplet under this SU2 left gauge group, there are other modes that can happen, and you see here top particles are in the final state, so they're totally different signatures. So directly you can actually check this. But one way to actually check this, and I'm really hoping that this will be announced soon, is to measure something else. Okay. So we want to distinguish models that explain RK. So now we see an anomaly, and we have several explanations. We can have SU2 vectors, or we can have SU2 triplet scalars of these hypothetical leptoquarks. And we want to know, okay, we want to pin this down. So the best thing to do is to measure, besides RK, the same thing, but with a vector in the final state. Now this is, you would say this is the same, it's both B to S. But there's a difference because it's a different spin structure. This is a pseudoscalar and this is a vector, and that means left-handed and right-handed couplings are treated differently in this decay mode. And this is exactly what these two different explanations do. They come with different weights of left-handed and right-handed couplings. Okay? So that means you can draw a correlation. So this is RK, this is 1, this is the standard model. And in green we have this 1 sigma band of the measurement, of this anomaly. Okay, and here on the y-axis we have a ratio of RK star, which is not measured yet, and RK. So this is a theory curve. So at 1, 1, we have the standard model. RK star is also 1 in the standard model. Okay, and in red, this is the prediction if these hypothetical particles are SU2 triplets, and in blue is a curve, it's a prediction if these hypothetical particles are a doublet under SU2. So red and blue can both explain RK. You can see this because they overlap with this green band. Okay, but they predict a different value of RK star. And I'm showing you this plot, which is really front-end science in this field, because LHCb is working on an analysis on RK star. So the important thing is RK star can be different than RK, and it can substantiate this anomaly. It will not be able to rule out this anomaly because with these different couplings it is possible that RK over RK star is not 1. It can be different. But this is really close by what is coming out of the experimental secret corners. So I'm not a member of LHCb, but this has been rumored that they are working on this, and it's probably coming out at some point.
Sorry, can I ask a question? I mean, how high do the states have to be around the platform? The scale, the lepton works. What is the energy scale?
Oh, it's above the surge limit, something like 1 TeV, and it doesn't decouple. So they cannot be much heavier than 50 TeV, which is beyond what we can do at the LHC, but it is not beyond what people are thinking about future colliders. So when you look at this Feynman diagram and you would be calculating this diagram, you would say the impact and low energies is the product of these two couplings divided by the mass squared of this particle. So the anomaly sets you the size of this product divided by the mass squared. So you can make the effect big by making the mass light, or by having the couplings large, or vice versa. But you need more information to resolve this ambiguity, and this comes from meson mixing. So actually it doesn't decouple. So if you say RK, this is a signal, it doesn't decouple. So how much time do I have?
You have 5 minutes, so because it will be typical 10 minutes discussion.
Yes, very good. Okay, so we are in the middle of Beyond the Standard Model Physics. We are in this flavor discussion, and this is an anomaly in the data, and it's linked to flavor. It is linked to a very very strong piece of the standard model, that's universality. Fermions couple universally to the gauge interactions, and apparently this anomaly tells you, if this is true, it tells you they are not. And if they are not, it's a breakdown of the standard model. It has very strong implications, so this is why we are very excited about this first measurement from LHCb, and of course this needs verification with more statistics. Okay, so you can explain this with these type of leptoquarks, and so there are different types. There are the doublets and there are the triplets. They have different decay modes. You could look for them at colliders, and also LHCb can distinguish these models, these two proposals to explain this anomaly. Okay, so what is the link with flavor? Of course, flavor is still, we haven't answered this question. If this is true, and we explain this with these hypothetical new particles, these leptoquarks, why do they couple different to muons than to electrons? We still have to break this symmetry. And now the symmetry breaking, which can't be coming from the standard model, has been just moved to this new particle. So that means we have to say something about flavor the flavor of these leptoquarks. And this is where things get really interesting. I mean, there's one thing to test the standard model, but it's a much bigger step to maybe approach a little bit towards this enormous problem that we don't know why the quark masses are the way they are on this flavor puzzle. Okay. So again, this is this Feynman diagram, and this is here we have these couplings, and they are labeled according to the flavors of the particles they couple to. Okay, and we can write this in terms of a matrix. And this is really the beauty of this particular standard model extension. It's a particle that couples quarks to leptons. That means that this coupling matrix has information about quark flavor in the rows. So it couples in the first generation, it coupled in the first row, it couples to the first generation quarks. In the second row, it couples to second generation quarks. Third row to third generation. Okay, but in the columns, we have the couplings to the different lepton generations. So if you want to explain RK, and you say, okay, all the anomalies are in the muons, you need the product of these two couplings. So it's a B quark to a muon and an S quark to a muon. If you say no, RK comes because the denominator is non-standard, so then you need a coupling from an electron to the strange quark and an electron to the B quark. But in principle, this whole matrix is filled, and you need a theory of flavor to fill this. But once you have now, assuming that this anomaly actually is true, there's a signal, you can actually probe this matrix. That means you can probe something that links lepton and quark flavor. This we don't have in the standard model. So this is the opportunity in this model. Okay, so again, the columns here, this is lepton flavor. Okay, and the rows is quark flavor. Now, we do have theories of flavor. We do have models that say, why are the leptons the way they are? It's just that there's more than one model, and it is difficult to rule one model out. Within the standard model, we can't do this. We need more models. There are many models that accommodate the masses that we measure for the leptons and for the quarks. Okay. So for the leptons, usually there's also a mixing matrix, and it's not hierarchical. It has order 1 entries, and that has stimulated scientists to explain to explain lepton masses in mixing with discrete symmetries. They are subgroups of SU3. Okay, so this is what we do for the columns of this matrix. We use discrete flavor symmetries. For instance, A4, which is the group of the tetrahedra. Okay, and it's a subgroup of SU3 because of 3 generations. And what this mechanism predicts, it fills this matrix essentially with zeros and ones. That's this feature of this discrete group that correctly can reproduce the mixing that we see in the neutrino sector. So for the rows, we know everything is hierarchical. We talked about this, the quark masses and the mixing, the CKM mixing matrix. So we use something else. So this is really something, a feature that's different between quarks and leptons. We use, this is called a so-called Froggatt-Nielsen symmetry. It's a U1 symmetry, and it creates hierarchies. So we need hierarchies among the rows. You need these models to explain flavor in the standard model, but the nice thing is now, we can predict now with these leptoquark couplings. So it's very easy with these theoretical tools to come up with a matrix like this. So this matrix essentially does exactly what you want. It couples B quarks to muons, and it couples strange quarks to muons, and the coupling to the strange quarks is a little bit suppressed, but this is because the strange quark mass is lower than the B quark mass. Okay, so within leptoquarks, you can actually probe flavor symmetries with these anomalies. So this is really an opportunity. So I don't know whether this anomaly will stay. If it goes away, then okay. If it stays, it really opens a window, because it's not just we are testing the standard model and the standard model broke down already. This is a super, super big thing. We can learn something about flavor because we are seeing breakdown of lepton universality in quark meson decays. So we have the opportunity to see some connections between these two different sectors, leptons and quarks. Okay. So this is one example where the road can go. There's this anomaly and there are other explanations, but this shows that if we actually see new physics, there's more than just that the standard model broke down. We can learn something about very deep problems like the flavor problem. You know, quarks are all food, and leptons are all food, and that's a symmetry because for the gauge interactions they are all the same. But of course they are not the same and their features are very different and we don't know why. But with these type of anomalies, we can, for instance, test whether this ansatz with an A4 and a Fock-Nielsen symmetry is consistent with data. So we are able to rule out flavor models. Okay, and with these words, I'm happy to stop and take your questions.
Thanks for tuning in for the next lecture. Now, questions.
Conclusions, but
Could this lepton quark also explain G minus 2 muon anomaly that
I
you
think
confirmed?
so, but there has been works done in the past. I'm hesitating because I'm not sure if this paper where G minus 2 has been addressed has not received some criticism. You know, there are different type of leptoquarks. You can write them in different representations under the standard model group. And some have been challenged by other experiments. But people have looked into this and I can point to the literature if you want. But I'm aware that there have been some kind of, okay, so people sometimes have overlooked some constraints and it may be that this was one of the papers. You can make a connection. You can also try to link these two anomalies that we've seen.
Other questions?
Is there a dark matter candidate in the lepton quark view?
Usually not, because the leptoquark is colored. So I think there can be. It's not a strict no, but it requires work to have a colored particle dark matter if this at all can be done. But people have linked anomalies. They have thought about Higgs to tau mu and RK with RD star. They have linked it with neutrino masses.
And are the hierarchies in the lepton sector and the quark sector, are they connected in some way through the lepton quark?
Well, the leptoquark is just a particle, but there's a link. Yes, they are linked. They are linked, so you can think about three terms: quark masses, lepton masses, and this leptoquark coupling. And all these terms, they involve two fermion fields. You can have two quark fields, two lepton fields, and you have one term with quark and leptons. And once you fix the quantum numbers of the leptons and the quarks, everything is determined. So there's a relation between all these three terms, and this is what I wanted to say. Because once you specify these charges, you can fix them by requiring that quark masses and lepton masses are fixed. You have a prediction for the leptoquark coupling, and then you can see whether it explains anomalies. So there's a relation. This is exactly what's so hot about leptoquarks.
There's a question on that.
What are the prospects for L2 to defend these actual parameters?
They will do it.
If the anomaly is real, to which significance can they measure it?
Oh, that I don't know, but they will be performing at least as good as LHCb. LHCb will be having at the end of run 2 higher signal rates. So for Bay2 it will take some time, but they are better with the electrons. So LHCb is they have about a factor of 5 more muon events than electron events. So on RK, the uncertainty is dominated by the uncertainty in the electron modes. So Bay will take some time to keep up with the muon statistics of LHCb, but they will be better with electrons. So if you wish, you can just measure the branching ratio for EE for the electrons at Bay2 and then combine.
But they will never get beyond 5 sigma.
That they can do, yes.
They can do, okay.
Yes, they can do this, but there are other measurements. It's not just RK. For instance, LHCb has only measured RK in this kinematic region of small q squared. They can also measure it at the high q squared. There's roughly the same event rates. I mean, it's a little lower, but it's kind of the same ballpark. But it's more difficult for LHCb because the electrons, they radiate, and then they have to see that the events are in the right bin and not move out of the bin and migration into this bin. But this radiation is not as problematic as Bay2. So yeah, they are also looking into measuring these mu to E ratios in other final state, as I said, in K stars, which is rumored to be coming out soon, which will be a very interesting number to know. But as I said, even if RK and RK star are not the same, it would suggest that there's beyond the standard model physics which has rate-and recurrence. So I would say it would be sociologically stressful if RK star turned out to be 1, but it's in a model-independent way you would say, okay, it means that we need PSM physics with rate-and recurrence. So I think the closest thing here is RK in all bins, better updates in all bins, RK star. They can also do R phi, everything that does D-IAS and dileptons. The other asymmetry, I didn't talk much about this with the tau mesons. That's an anomaly between tau leptons and others, and it's induced in the standard model at tree level. So to have a large BSM effect on something that's already large in the standard model, this requires really, really large new physics. So that, I think, needs to get more into thermal equilibrium, but of course this also will be pursued at Bay2. Bay2 will be very important for this.
So the leptoquark model, what is the dependence on Q squared of RK?
Oh, it's for RK it's roughly the same. It's not a big difference. I mean, in the standard model it's 1, and because in these leptoquark models, what you are inducing are these 4 fermion operators. Operators with a B quark, a strange quark, and 2 muons. And they are dominating. They are dominating except at very small q squared where there is a dipole contribution, which goes like 1 over q squared. Okay, but that's as when you move out to higher q squared, that 1 becomes less and less relevant. So roughly to first order, it's the same with PSM.
Any further questions? Yeah, please.
Just a question about, do you know what is time scale when you will have the answer for the car star coming from the LHC or?
From LHCb, okay, so there's a Morillon conference coming up. This is one of the bigger spring conferences, and okay, so it could be that RK star is presented the first church, but this will not decide this, which will just add another part. When they update RK, I don't know. Bay2 is starting 2007, this year, next year, then it takes, okay, so they start running and they have to accumulate enough data. As you saw, the branching ratio is 10 to the -7. They need a lot of events to have that reconstructed. I mean, there's a lot of events that they don't, there's more bees than they can actually analyze. So it will take a few years. It will take a few years from now.
And could you comment on how comparable are the different places where you can do experiments? like the L and BABA and LHC, can you compare the results, or do you know that there are some things in the experiments that are different and that might lead to some bias in the results you get, or?
Okay, so Bell and Baba are not running anymore. These experiments, they have been shut down some time ago, and whenever there's new data, they just reanalyze new data, but they were actually they are limited by statistics. They are really trying the best they can, but ultimately LHCb has passed them already in terms of statistics. So they are adding something to this picture in terms of consistency, but they cannot dominate the situation anymore. So there was Bell and Babar, and now there's Bell 2 at the horizon. So Bell 2 will start. So Bell 2 is an experiment at an E+E- collider, and that is what people call a clean environment. You know, the LHC collides protons, so protons collide, and there's a lot of stuff. I mean, there are pions produced and pi zeros, and they decay, so there are photons from all over the place. And now we have B2K EE and electrons, they also radiate. So the LHCb is a more complicated environment, but of course they have high event rates, and they are producing really, they have high luminosity, they have really large number of big quarks. So for them, the electron modes require more simulation than the muon modes. So this is something that is discussed. In their paper, they explain how they check their results. So there's a decay that's very frequent. The B meson decays through a J psi, and decay in the J psi, it's a resonance, decays also mu and EE. And that's a branching ratio of 10 to the -3. So there they have lots of events. So on resonance, they checked that the ratio is 1. So this was their test that their reconstruction of electrons is correct. But then it's an extrapolation because they are not at 10 to the -3 rates, and it's a different kinematical point. Okay, so this is what they did. So it's the first measurement with electrons at in the LHCb experiment. So they were pushing really hard, and I think it's a very interesting number, but it's it needs validation, and LHCb will work on this, and I think because this number is so important, it needs an independent check. So there's LHCb and Bell 2 for this anomaly.
Since the food is waiting, and you can ask for the questions upstairs, let's thank again Gudrun.